We talked a little bit previously about Lewis dot structures, and so let's continue on talking about Lewis dot structures and lead into valence bonding theory as a way of talking about how molecules form bonds. But before we get too deep into that, let's just talk about a couple deviations from the octet rule. The octet rule is really a guideline. As you know from previous examples, always and never aren't really in my vocabulary when it comes to chemistry. It's always about the exceptions. There are lots and lots of deviations from the octet rule. Radicals are one of the primary examples. These are materials with unpaired electrons, electrons that are either odd number of electrons or materials that have electrons that are unpaired with respect to one another. The way we are going to see this mostly is if they have an odd number of electrons. And when we see it, we usually see it as a mistake. And if you're adding up your totals and you have an unpaired electron, uneven, you should usually end up with an even pair of even number of electrons. So if you end up with an odd number of electrons, you usually have miscalculated. And this usually shows up in the form of charge. In other cases, we'll find elements, particularly things like aluminum and boron and gallium, that deviate from the octet rule. They're perfectly happy having 6 valence electrons. Boron in particular doesn't really need all 8. It's very happy with 6. And the reason for this is it's small, and there's a couple of exceptions to this. And almost the most common one that we're going to see is when things have too many electrons. That is, they have greater than 8 valence electrons. Almost every element with a mass greater than aluminum can form compounds that have an expanded octet. And we'll see that over and over again. We can still use our valence electron rules to draw these structures. And most of the deviation will show up on the central atom. So those are little gotchas that you'll see. How we can use Lewis dot structures to predict shape. When you put electrons around an atom, there's only 5 basic geometries that you can access. So we can have a structure that's sort of where we have 2 electron geometries. So we have 2 electron regions. Now, electron regions can represent bonds, can represent atoms, can represent lone pairs, but we're just going to talk about regions. 2 regions. A good example of this would be a molecule that has the following structure. This would represent a linear arrangement of atoms, and the bond angle between these regions would be about 180 degrees. No about it. It would be 180 degrees. So what do these look like? Again, there's nothing too surprising. They look like like a barbell with the the 2 regions separated by a distance of an angle of 180 degrees. Now, you can put 3 regions around that atom, and that would take the form this is a trigonal planar region. Trigonal to represent 3, and planar to represent that these electron regions are all within the same plane. This would represent a 120 degree angle around those of the electron regions around those atoms. we can see this in this example. Again, notice how all three of the atoms are very flat. The central atom is within the plane of those three atoms, and it forms a triangle with respect to the three outermost atoms. This is a trigonal planar arrangement. One of the most common ones is the tetrahedral arrangement, which is difficult to draw. But when you place four things around an atom, they don't flatten out like the trigonal planar. Instead, they pucker, and you end up with a tetrahedral arrangement. Where these dashed and dotted lines are used to sort of represent how they stick above and below the plane of the paper. It turned out the angle between these is 109.5 degrees. This is a tetrahedral arrangement. And it's called the tetrahedral arrangement because if you connect all four of the compounds, they form a shape called the tetrahedron. Again, not very easy to draw on paper, but easy to illustrate in 3 dimensions using a model. A central atom with the 4 components forming an equidistance from the central atom to form this tetrahedral shape. If you connected all the vertices, it'd look like a little pyramid, a triangular pyramid. Right? Although we usually don't call this a pyramidal structure. This is called the tetrahedral geometry. And again, the angles are 109.5 degrees. Now, there are 2 other arrangements when we start to get beyond. And unlike previous examples where all the bond angles were the same, this particular one has 5 regions around it and happens to have different bond angles depending on whether we're around the equator of the compound or whether we're on the axes. So the bond angles between these regions are 180, or between these ones, they're 90. But within the central region, the bond angle here is 120 degrees. And this is another way of representing it. And this is described as the trigonal bipyramidal geometry. And lastly, we have when we have 6 regions around the central atom, it turns out that all of the bond angles between these areas represent 90 degrees. And because chemistry hates you, this geometry is called the octahedral geometry. And the reason it's called the octahedral geometry is because if you connected all of the sides, if you connected everything, you would form what is called an octahedron. square central region, square axes. For those of you that play Dungeons and Dragons, this would be a D8. All right. So it's an 8-sided die, octahedron. So let me show you these two structures. So here we have our trigonal bipyramidal. Again, we can see the central axes, and then the linear arrangement, where the bond angles here represent 120 degrees, and the bond angles there represent, along these axes, represent 90 degrees. And we can see something similar for the octahedral arrangement, though all of the bond angles are 90 degrees. So these are the 5 basic geometries upon which everything else is generated. All right. Now, just because something has 5 things around it doesn't necessarily mean that it's going to be trigonal bipyramidal. And so what we have to, again, this applies to electron regions. So we have to use the electron regions to guide us. It turns out that there are a wide range of other shapes that arise depending on how many substituents are present around that central atom. Right. So we'll use these as our starting points to describe the rest of the shapes.